So hello everyone and welcome to the Mário Schenberg Group YouTube channel. Today we have the pleasure to talk with Professor Clifford Martin Will from the University of Florida about his academic trajectory. Good morning, Professor Will. How are you doing today?
Very well, thank you. Thank you for having me on your recording.
It's a pleasure. So I would like to begin with some questions about your early life. Okay, so where did you grow up and what was your family background?
Right, so I grew up in Canada in a city called Hamilton, not far from Toronto. My parents were working class parents. They worked in various factories in the town. But I did very well in school at an early age, and so they assumed that I would go to university and proceed that way. So I went to college at a place called McMaster University, which is a well-known university in Canada, in my hometown. So I could just drive there, or I didn't have to go away for college. But when I graduated, and I was a physics major there, I graduated from there in 1968, and it was clear at that point that I wanted to do theoretical physics, and pretty much the future, if I wanted to pursue that, was to go to the United States. There were excellent universities in Canada, but really, for theoretical physics, America was the place to go. So I graduated and applied for graduate school in the US.
Right. So, still in your early life, can you talk a little bit in more detail about your parents, where they're from, what are their names, etc.?
Yeah, so my parents were both born in Canada. I think my mother's parents, my grandparents, were born in England. And on my father's side, there was several generations before that. They were born in the United States, and we trace our family back to France, maybe Holland. So it's a little fuzzy. I've not done a serious search of all my various roots.
Okay.
But yeah, and Hamilton at that time was a industrial city. Several major steel plants, a soap manufacturer, Procter & Gamble, famous soap company. So it was mainly a working class city. And so that's how I grew up, in a working class neighborhood. We did all the usual things that kids did in the 1950s and 1960s. Of course, a very different world than today's world.
Of course.
For the kids growing up.
Good. So what were your schools like before university?
So I attended a high school. It was a small high school because it was built on the edge of the city in anticipation of people, moving into the suburbs. The city was expanding. So at the start, the school was quite small. Later, as more families moved into that suburban area, it got bigger. But at the time, for example, in this high school, there was one science teacher. And I took from him chemistry, basic science, physics, chemistry. So in the 11th grade, I took physics. In the 12th grade, I took chemistry. And in the 13th grade, in those days, Ontario in Canada had 13 grades. So in grade 13, I took both physics and chemistry, two separate classes. And I also took at the same time 3 mathematics classes: algebra, geometry, and trigonometry. This was, of course, before they began teaching calculus in high schools. Calculus in those days was strictly a college topic. But it turns out that this teacher was absolutely excellent and really inspired me to think seriously about science. I already knew by about the 11th grade that I wanted to do science, and mainly physics. I read a number of popular books about astronomy and particle physics and so on. So I really knew physics was what I wanted to do. So I took all the courses I could take in high school. But this teacher was just so inspiring that he really convinced me that I was doing the right thing.
Okay. So, moving to university now, so what did you study as an undergrad, and where did you attend university?
Right, so this university, McMaster, is just right in my hometown, so I could drive there just for daily classes. And I lived at home until my senior year. I'm sufficiently, I'm noted for planning things in advance and organizing things. So I already knew by my junior year that I would probably be leaving and going to the US for graduate studies. So I thought it'd be a good idea to leave home and get practice living on my own. So in my last year of college, I rented an apartment with 3 friends, and we, learned how to live on our own for a while. Just from my point of view, in preparation for moving a long distance, possibly a long distance away. But in McMaster, I remember very clearly in the lineup, in my first day of freshman year, first day, there's a big line, and they asked me what I wanted to do, and I said, I'm signing up to be a physics major. I didn't have to wait till junior or senior or sophomore year. I knew right from the start, I'm going to be a physics major, and that's what I'm doing. So I took all the basic classes, freshman physics, freshman chemistry, various other elective courses. But by second year, I was taking several mathematics courses, probably 2 physics courses, and then as each year I just took more and more math and physics courses and fewer, non-science courses. I took, sort of all the usual things: solid state physics, nuclear physics, mathematical physics. I took linear algebra, a whole range of applied mathematics courses. In fact, my formal degree from that university is in what's called applied mathematics and theoretical physics, which is a degree really dates back to England. So I just took as few experimental or lab courses as I could possibly imagine, because I really hated experiments. The only good thing about the lab courses was my ability to invent elaborate theories to explain my lousy data.
So can you pinpoint the point where you decided to be a researcher, and particularly a theoretical physicist? So was there any doubt in your mind in your undergraduate years about this?
Right. So already as an undergraduate, I knew that theory was what I wanted to do, as opposed to, say, being an experimentalist, which is a whole other kind of physicist. But I just knew that my deep interest was more on the theoretical side. And so, and that was almost from my freshman year. But as the years went on, it was even clearer that's what I was going to do. And so when I began thinking about graduate schools, I focused on ones where there were very strong, graduate programs in theoretical physics. They might have had lots of experiment, but I really focused on ones that were where I knew they were famous for theory.
Great. So now moving on to your graduate years. So where did you go to earn your PhD, and who was your supervisor? How do you meet him?
Yeah, that's a bit of a story. So I applied to many different places in the US, plus a few backup schools in Canada where I knew I would surely get in. So I applied to Princeton, Caltech, Cornell, all the big famous, American schools for physics. And I got into all of them, actually. But in the end of the day, Caltech appealed to me more, and so I accepted going to Caltech. Also, it was California, is very different from Ontario, Canada, nicer weather. So there's a great appeal to just going to California and seeing what it was like. But of course, in those days at Caltech, they had Feynman and Gell-Mann, very famous theoretical physicists. And so that's where I ended up going. However, I ended up, of course, my PhD advisor at Caltech was Kip Thorne. But when I arrived at Caltech, I had no idea who he was, or even that he existed. He was a very new member of the faculty. He had just joined Caltech, returned to Caltech from his PhD at Princeton. He was an undergraduate at Caltech, went to Princeton for his PhD, and then came back to Caltech. And at that time, he was a professor, but he was only 28 years old, very young.
So what year was this?
This was 1968. I arrived in the fall of 1968. So Kip was 28. But I didn't know anything about him because he was so new that the brochure that Caltech sent me describing all their research, they hadn't updated it to include him. He was so new. So I arrived not knowing anything. But it turned out there were a group of Canadian graduate students already at Caltech, and so they kind of welcomed me and helped me navigate things. And at some point they said, well, what do you want to do? I said, well, I do theoretical physics, but I'm not sure what kind. And he said, well, there's this new faculty member. He's kind of weird looking, red hair. And, you've seen pictures of Kip in the early days. He really was a kind of geeky looking guy. And he has this weird name, Kip. That's a kind of strange name. I said, well, I've never heard of him. Well, they said, go talk to him. The problem was that this was about, I'd been there a month and a half already. So I went to talk to Kip, and he said, well, if you're interested in general relativity research, it's too bad, you're out of luck, because I'm teaching the general relativity course now, and we only teach it every other year. So if you don't take it now, you'll have to wait till your third year, and that'll be too late. So I very quickly went to the registrar, and I dropped an astronomy course that I had signed up for Kip's course. I had to work to catch up with a month and a half of work to, get up to speed. But finally I did. And during the course of that course, I did, I guess, pretty well. I wrote a term paper on equations of motion in general relativity that I guess impressed Kip. And so by the end of the year, Kip asked if I would be interested in beginning to sit in on his group meetings to see if this was something I'd like to do.
Okay, so what was the climate in these meetings, and in the what were Kip as a supervisor? How was your experience with him as a supervisor throughout your PhD years?
Right. So you have to understand the history of the subject to know that by the 1950s, general relativity was considered a subject that no self-respecting physicist should study. It was really in the backwaters of physics. There was no interest in the subject. Nobody thought it would ever have any importance for physics and astronomy. But by the early to middle 1960s, relativity was starting to rise, mainly because of the discoveries of quasars, pulsars, the cosmic background radiation, and so on. People started to think that general relativity might be important for astrophysics. And so when I arrived at Caltech, this was just at the beginning of this, what I call the Renaissance recovery, or the return of general relativity. And Kip was very active in developing this whole new revival of the subject. So, his students were working on problems like perturbations of black holes and the gravitational waves they would emit, whether or not the redshifts of quasars could be explained by imagining the quasars were super dense clusters of stars, so that the redshifts were gravitational redshifts of the light coming from this dense cluster. One of Kip's students at the time proved that that was impossible, because to get such high redshifts, these clusters of stars would be unstable and would collapse to form a supermassive black hole. So these kinds of questions, not so much about the mathematical details of GR, but about what was it telling us about observational astronomy? Those are the kinds of questions that Kip was asking. But then, in June of 1969, so I'd just finished my first year and was sitting in on Kip's group meetings. I had no clue what anything was about. I mean, they were all talking details of what they were doing, and I had no idea what they were saying. So I was very new, just learning. But that June, Joseph Weber, an experimentalist at the University of Maryland, announced in the New York Times, plus in physical review papers, that he had detected gravitational waves. Weber was using these big cylinders of aluminum and detected the vibrations of the cylinders as a wave passed through. But this was an absolute crisis for the field, because if he was right, no one could imagine what kind of source could produce waves of that strength and of that frequency. In terms of, he was seeing events sometimes several per day, several per week, and no one could imagine what could be producing events at that rate and at that amount of energy. So that's why people started working a lot on trying to find exotic sources for gravitational waves. But Kip asked himself, well, all these estimates of what the waves should be like rely on general relativity. If Weber's right, maybe general relativity is wrong. Maybe this is a test that general relativity has failed. And so, and I remember this fairly clearly, I was sitting in the group meeting, and Kip looked around the room and said, and pointed at me and said, Clifford Will, this summer I want you to go out and find out everything we know currently about the experimental tests of general relativity. How valid is it experimentally? Because maybe Weber is telling us that it's wrong. And Kip was very worried. So that I did that. I spent a summer doing that, and that really launched my 50-year career on thinking about how we can test general relativity better and better, and with newer methods. Of course, these days with things like gravitational waves.
Great.
The other thing about Kip, of course, was he was an absolutely charismatic and inspiring teacher. I mean, all of his students just loved him. And years later, after he won the Nobel Prize, a bunch of us organized a surprise party for him in Pasadena. I mean, we just all, he was such a great man, kind to his students, concerned about his students, also taught us so much about how to do physics, how to do physics in an ethical manner, how to communicate physics. He wrote many popular books and inspired me to write some of my popular books. So he was just an inspiring guy. We all love him.
Great. So after your PhD, how did you keep researching? What were your interests in research, and how did you develop then? Maybe the first years after your PhD.
Yeah. Right. So after my PhD, I tell this story today. Young physicists are astounded at the decision I made. So after I got my PhD, I had basically the main two job offers I had were a tenure track assistant professorship at the University of California, Santa Barbara, with Jim Hartle, the very famous relativist, or a postdoctoral fellowship at the University of Chicago in Chandrasekhar's group. So choice between a tenure track professorship and a postdoc, and I selected the postdoc. Today, students go, what? How is that possible? two reasons. One was at the time, University of California, Santa Barbara was a fairly small physics department, not very well known. The only well-known person really was Jim Hartle, who was a fantastic guy, great relativist. Whereas at Chicago, there was a big group of Chandrasekhar, Bob Garrosh, a very famous mathematical relativist, and Jim Etzer, one of Kip's former students, who was a great friend of me and my wife. He was also in the department, and had a big astrophysics department. So to me, I thought, and in those days, we all felt very optimistic about our careers. We could see that this was a growing field, and that somehow, whatever choices we made, it would all come out okay in the end. So I chose the postdoc, which today would be a strange choice because of just how things are different today. So I went to Chicago, and but I mostly continued my work on experimental tests of GR. Was in the middle of writing up some lecture notes for a big review article. I had many other projects involving tests of GR to work on, and so I tended to continue with my own work. I did a little bit of work in collaboration with Chandrasekhar, but mostly I did continue with experimental tests of GR type topics. For 2 years, I was there as a postdoc. I was actually an Enrico Fermi fellow. It was a fancy kind of postdoc.
Right. So, if you had to choose your most influential mentors or collaborators throughout maybe the early part of your career, of course, Kip and Chandra, of course, will be there, right?
I always talk about there are three people, and I'll introduce you to the third person in 1 second. So, of course, after Chicago, then I was serious about applying for faculty positions, and I was offered an assistant professorship at Stanford University back in California. And, of course, the main person there at the time was Bob Waggoner. He was a well-known already astrophysicist. He had been a postdoc at Caltech, although we never actually overlapped. But he had worked with Willie Fowler and Fred Hoyle doing the first full serious calculation of Big Bang nucleosynthesis, working out the relative abundances of all the light elements that would come out of the Big Bang. So that was around 1967. So he was already famous for that really famous groundbreaking calculation that really set the stage for a lot of the cosmology work that came later. And because of Weber's claimed detection of waves, Bob Waggoner had also started thinking himself about gravitational waves. And so that combination seemed to me ideal. And Bob was just a fantastic guy to interact with. He is one of the most enthusiastic physicists I've ever met. Just full of life and vigor and enthusiasm. And, this is so great. And, just the kind of, his attitude was, if you're not having fun doing physics, then you're in the wrong field. Do something else. So he was very influential just in terms of how to live and enjoy doing physics. So I really talk about those three main mentors. Kip really taught me about GR, taught me about communication of physics to the general public. Chandra taught me about doing very detailed, meticulous calculations and keeping track of things, which I've done a lot of later in my career with post-Newtonian theory. These days, of course, we have Maple and Mathematica to help us. He did everything by hand. It was unbelievable. And he also taught me a good sense of history, Chandra, because of his age and his experiences with Eddington and some of the famous scientists of earlier in the century. He had told me lots of stories about history. And so I really developed an appreciation for the history of our field. And then Bob just taught me all about how to have fun doing physics. So I'll give you an example. I was just arrived at Stanford. I was still setting up my office and starting to get down to work. This is middle of September 1974. And Bob came rushing into my office, waving a telegram. There's a special telegram called an IAU telegram. So young people, of course, don't even know what a telegram is, right? Because it's, it's not a WhatsApp. But it was these are telegrams that in those days were sent out by the International Astronomical Union to announce new discoveries in astronomy. They were sent to all the other observatories and other universities and institutes around the world so that people could very quickly learn maybe a supernova had been detected or something. This actually exists, but they don't send telegrams anymore. It's just posted on the internet with suitable alerts. But he came in waving this IAU telegram and he said, "Cliff, whatever you're doing, you got to drop it. They've just discovered a binary pulsar. We've got to work on this. This is the most exciting thing. We got to get going on this." So this was, of course, was the famous Hulse-Taylor binary pulsar, a pulsar orbiting another star, which we now know is also a neutron star, but no longer a pulsar. And it was clear right from the start that general relativity would play an important role in the orbit and evolution of this system. So within a week or so, Bob and I we didn't collaborate, but we decided to write two separate papers on different topics related to, Bob wrote a very important paper on the damping of the orbit due to gravitational wave emission. He worked out the formulas and estimated how long it would take at that current level of accuracy to measure the effect, the shrinkage of the orbit due to gravitational wave damping. He estimated it would take about 15 years of data to measure this tiny effect. It turns out, of course, Hulse and Taylor beat that. They did it within about 5 years, mainly by improving sensitivity at the detectors and also by improved data analysis techniques. And I wrote a paper having to do with the advance of the pericenter of the orbit. The orbits are eccentric, but the ellipses rotate. And I wrote a paper on the implications of measuring that for alternative theories of gravity, how you could test general relativity by measuring that effect. So there's a flurry of activity during that fall. Hundreds of papers were written on many aspects of that binary pulsar. But so this was a very exciting time, and it was Bob who just really forced me to just not sit in my chair, but actually get going.
Terrific. So now moving on to your many books, the books you have written, both the textbooks and the popular books, the popular science books. So they have made a remarkable influence in the field, right? So did you imagine this impact that your books would make when you first wrote them?
Yeah, not really. It was sort of one book at a time. The first book I wrote, this is my sort of textbook on experimental tests of general relativity. I wrote that around, during the period 1979 to 1981. And really, it just put together all the work I had done and others had done. Talked about the various formalisms for studying tests that I worked out in my PhD thesis and other things that other people had done. So it's a monograph giving all the gory details of calculating what alternative theories predict and comparing those things with experiment. This is my book, Theory and Experiment in Gravitational Physics. So that was a very technical monograph, and I felt it would prove to be useful for the field. Young people, graduate students could read it and get involved in the field. And it turned out to be a very successful book. Later in 2018, I wrote a very major revision of it, a second edition, brought it up to date with the gravitational wave detections. So I really rewrote the whole book to some degree. And then it was around this time, 1981, that I moved from Stanford to Washington University in St. Louis. At Stanford, I'd been an assistant professor, an untenured position, but at Washington U, I arrived already with a tenure. Within 4 years, I was a full professor. 4 years later, I was department chair. And so, idiocy, I agreed to be chair, and I was department chair for 10 years. But anyway, but around 1985 or so, I started thinking, this story of tests of general relativity might be of interest to the general public. It's hard writing about physics to the general public. Physics is such a technical field. There's a lot of jargon, there's a lot of mathematics, some of it very abstract, and it's really hard to reach the public. But in this case, you can downplay the detailed theory and just talk about the experiments because people sort of understand the experiments, sending spacecraft, something in the laboratory, they can visualize it. And also, over my career as a graduate student up until that time, I had sort of been present at many of the experiments. I knew personally many of the people who had done them. They had told me stories about, how one of the atomic clocks wasn't working and they couldn't get it to work right. So they just held it above the ground and dropped it. And the impact obviously dislodged something and it started working again. So I had lots of stories and anecdotes that I could tell to make the thing more interesting. So I decided to write a popular book. And this is my Was Einstein Right book, published in 1987. And really, it took me about 9 months to write it. It was very fast, partly because everything I knew, I just put down on the page. I had lots of stories to tell, lots of simple explanations for the experiments and what they were measuring, what it meant for general relativity. And it proved to be, well, for a science book for the public, it did very well. I like to say that it put my younger daughter, it paid half of her tuition at an Ivy League university. So.
Oh, that's great. So.
Then, of course, later, if you want to cover the books, later on, of course, okay. I moved to the University of Florida, and by that point, of course, we were all working on gravitational waves and post-Newtonian theory, equations of motion, to higher and higher orders in a post-Newtonian expansion to achieve the accuracy that was needed to analyze data at observatories like LIGO and Virgo. So we were being pushed by experimentalists to do these higher order calculations. So at some point, my friend Eric Poisson, who I'd known for many years, contacted me and wondered if I had ever thought about writing a book on sort of details of post-Newtonian theory. And I sort of had, vaguely, I'd been giving lectures about it. And so we agreed, let's just write a book. And it's now this giant, thick thing. We call it the Bible. But it has also proven to be very useful to again, younger people. You can really learn, if you want to get into gravitational wave science, you can really learn everything you need to know from that book. And I say that in all modesty, but we really wanted to make it useful and pedagogical so that people could study it and learn. Every chapter has between 10 and 20 problems and exercises for students to work on and so on. So that was a lot of fun. It took us a while to do it, but we're very, very pleased with that book. And then very soon after that, I did a complete update of my earlier theory and experiment book, mainly to bring in all the new data, information about gravitational wave detection as a way to do tests of general relativity. And then a few years after that, Nico Yunus, a former student of mine at Washington U, a former undergraduate student at Washington U, is now very famous director of the Cosmology and Gravity Institute at the University of Illinois, he and I decided to write a book called Is Einstein Still Right? But a popular book of the same style as my earlier Was Einstein Right book. But now again, we can bring in all the newest results from gravitational wave detection, imaging of black holes with the Event Horizon Telescope, and so on.
That's great. So if you had to pick one, what do you consider your most important scientific contribution?
Well, I'd have to pick two.
It's okay. You can make it top three if you want. Top five.
So, I mean, the work I did really, right in my PhD thesis with Kip, it was based on earlier work done by a man named Kenneth Nordtvedt at Montana State University, but I was able to generalize his result, and later Nordtvedt and I combined our two versions into a canonical version. But it was this framework for studying alternative theories of gravity and at the same time analyzing experiments. It's called the Parameterized Post-Newtonian framework. And it's sort of become a working tool for many people for many years, working in tests of GR. And so it had a big impact in the field. But the other thing was later on in the middle 1990s, when we were all starting to think about the future of gravitational wave detection by the ground-based detectors, which then were still under construction. In some cases, still getting the final funding for construction. But it was clear at that time that in order to do the best job of analyzing the signals that come in and getting science from those signals, we would need very accurate predictions from general relativity. And so in 1993, Kip held a workshop at Caltech on this very problem. How do we get these accurate predictions from general relativity ready in time for the first detections, which might take place 5 or 10 years in the future? It was actually 15 years in the future, but it actually did come. But it was a big challenge. I mean, it was a very tough problem. One part of it involved numerical relativity, solving Einstein's equations on the computer to understand the details of the final merger of the two black holes. And that was largely unknown how to do that at that time. And the other was the early part of the inspiral, when the bodies are still far apart, moving at high speed, but still governed by what's called post-Newtonian theory, these approximation techniques. But you had to go beyond the lowest order to get this part of the orbit accurately. So as a result of Kip's workshop, two groups, my group in St. Louis and the group in Paris, headed by Thibaut Damour and Luc Blanchet, we agreed to collaborate on working out the next order, called the second post-Newtonian order, for the gravitational wave energy flux. This is a major challenge at the time. Today, it's kind of, today we cover it almost in Fossil and Will. It's almost a textbook. But at that time, it was very tough. So the two groups, we agreed we'd work separately. We wouldn't talk to each other as the calculation was going on, because we didn't want to influence each other. We would only compare our results when we got a final result. And then we could compare the results. And so at the end of the day, we were, my group with Alan Wiseman, we were a bit behind the French group, about 3 or 4 months behind. So they said they were ready. We had to finish final details. And so we had agreed upon what the answer was we were going to compare. And you've seen these expressions with these large rational fractions, 21,375 divided by some enormous number. So we had formulas that had some of these strange rational fractions. And so Alan and I typed up the answer. This is primitive email in those days, so we had to fax the answer to Paris. But because of the time difference, it was already night in Paris, so we had to wait until the next day to get the answer. So we were, chewing our nails overnight. But I sent the answer back. every single coefficient was in agreement with theirs. I mean, it was like fantastic, fantastic moment. But of course, that the result had a big impact, largely because it proved that the techniques we were using could be then carried on to higher order. And this was mainly done by the French group. They had more sophisticated techniques than we had in our group. So they carried on going to 3p order, 4p order, 4.5, tails of tails. So they've really advanced the field tremendously. But I think our paper showed, kind of was the spotlight that showed the way to do it and how you could move forward. So those two are kind of the things that I seem to have had the best influence. And years later, when I was elected to the National Academy of Sciences in the USA, those are the two aspects that were part of the citation for my election. So I was very pleased for all.
Fantastic.
An honor, to be sure.
Of course.
An honor to be elected to the NAS.
Of course. So moving on to questions about frontiers in physics and science. So what do you think are the most important experimental and observational tests of general relativity, maybe historically wise or today?
I mean, I think there are sort of three aspects that are important and ongoing, and in the future, hopefully, will tell us much more about general relativity and its limitations or any corrections that have to be made to it. One is still testing the weak field limit, primarily in the solar system. There are still experiments going on, mostly using advanced techniques to analyze planetary data on orbits of planets and satellites that are becoming so much more accurate and sophisticated, plus additional data from missions like Bepi-Colombo, which is about to send 2 orbiters around Mercury, which will improve our knowledge of Mercury's orbit by a huge factor. So I think there's still a lot to be learned in terms of testing GR from the solar system, largely because we understand the underlying physics to a large degree. So you can get clean results that test the gravitational theory. The second aspect, of course, is just gravitational wave detection. I mean, this has really revolutionized, brought us new tests of general relativity in the dynamical, strong field regime, which is very different from the solar system. And there have been many tests, there are many papers, not a single inconsistency with general relativity so far, from hundreds and hundreds. I think it's up to about 400 detections now from the LIGO-Virgo-Cagra collaboration. And a big part of what they do is to run all of the new data through a sequence of tests that they've built up in the data analysis pipeline to get better and better and better tests of various aspects of GR. Then I think the third aspect is on the grandest scales, the effort to understand whether or not the effects that we attribute to dark matter are really due to some kind of massive or maybe not so massive elementary particle, and whether the acceleration that we detect in the universal expansion is due to something like a new form of matter called that everyone just calls dark energy. We don't know anything more about it, so or whether it implies some kind of modification of general relativity that only kicks in at these largest scales in the universe, but otherwise on the scale of gravitational waves and solar system are too small to be observed. Theoretically, that's a big challenge, it turns out. It's hard to modify general relativity in that way. Somehow, if you tweak it to do something on the large cosmological scales, something comes in the back door to produce some unhappy effect on the small scale that you have to somehow suppress or figure out. So theoretically, it's a very big challenge. I have many friends who work in this area, and they always say, as soon as you, general relativity surely must be the correct theory of gravity. It's so simple, and as soon as you try to change it in any serious way, all horrible things. It's like Medusa. You cut off one snake from her head, and 10 more snakes pop up. So, so it's a big challenge. And of course, just on the observational side, it's a big challenge just because it's hard to separate the gravitational, any modifications of gravity from just the basic environmental things, and the fact that the data on these scales is different from, it's not as clean. There's lots of astrophysics you have to think about. So there's lots of observational challenges as well. But who knows? It may either help us to give more confirmation of GR or point us in the direction of how to modify it.
Great. So, Professor Will, do you think we will eventually detect gravitational waves from the S stars orbiting Sagittarius A star? Is this a plausible thing to expect? And maybe what is the time scale of this detection?
I don't think you'll ever detect gravitational waves. I think the signals are way too weak to be detectable. I haven't done any detailed calculations myself. I'm sure many people have. But I think because these are just, 10 solar mass type stars, the signal will be very, very weak. I think the importance of the stars orbiting the black hole at the center of our galaxy is to look for the other general relativistic effects that are associated with that black hole and how they influence the orbits. So, for example, years ago, I suggested that if you detect stars orbiting that supermassive black hole that are much closer than the current ones that we've seen so far, orbiting maybe with a period between a month and a year, rather than the tens of years for the S stars, then these stars will be close enough that their orbits will be influenced not just by the effects associated with the mass of the black hole, but they'll also be influenced by the frame dragging due to the rotation of the black hole, also be influenced by the quadrupole moment of the black hole. And if you could detect enough stars, I showed you could, in principle, separate the effects of frame dragging from the quadrupole moment, and thereby separately measure the quadrupole moment and the angular momentum of the black hole. And that would be a test of GR, because we know for black holes, there's a very exact formula that relates those two quantities. In fact, Q, the quadrupole moment, is equal to the square of the angular momentum divided by the mass in suitable units. If you don't see that, then that is a violation of general relativity. And this is something that people who are involved in these observations, Andrea Gez's group at UCLA and Reinhard Genzel's group in Germany, they've taken on as an important science goal to try to do this, what I call a test of the no-error theorems. But it's a big challenge. Seeing stars much closer to the black hole is very tough. It requires big improvements in the telescopes, being able to track the stars, and involves lots of improvements. But they have it in their minds that they might one day be able to reach that goal. Also, you just have to detect the stars that close. Maybe there aren't any. We don't know. Simply have no idea. No reason why there shouldn't be, but because even though the black hole is not very bright, whatever accretion is going on to that black hole, it's very, very thin. So, but it's bright enough to make it hard to detect stars orbiting closer. You just have this background brightness that makes it hard to detect the stars. But maybe they'll detect a couple one day. You never know.
I see. So, do you think we will ever obtain experimental evidence for quantum gravity, or perhaps detect the graviton directly?
No.
Would you like to expand on that a bit?
I mean, it's impossible. I mean, there's a lot of talk, but I find I'm just very skeptical of we'll ever be able to do. The effects are simply so weak at the quantum level. I mean, the only sort of possibility that might might give a clue is if in some models of quantum gravity that through the Big Bang evolution they leave some sort of imprint on something that we might be able to detect, like the nature of the fluctuations in the cosmic background. But even these are a stretch. You have to stretch the fundamental parameters, very far in one direction to get something that's observable. So, and the idea of detecting of graviton the way we can detect single photons is just impossible under any kind of scenario, in my opinion.
Okay, so final question, Professor. Would you like to leave a message to young students and researchers?
Well, I believe the message that I often leave to, I used to give to graduate students who wanted to come and work in my group. Even though this is, in my view, one of the most exciting fields of physics, it's still a very small field when you compare it to condensed matter physics and chemical physics and biophysics. It's a very small community. There are not, relatively speaking, many jobs in GR research compared to bigger university physics jobs. And so it's very likely that somebody coming to do a PhD in GR will have to graduate and find a job not doing GR. Maybe some other part of physics, maybe computer science, and so on. But my message is that if you are prepared to really have a broad understanding of many areas of physics, have very good computer skills, that's essential these days, but if you're willing to spend 4 or 5 years doing gravitational physics, you will look back at that as being the most fantastic and exciting time of your life, even if you ultimately go off and do work in other fields. And I've had students who have gone and had very successful careers working in areas that are not part of general relativity, but they've used their training as physicists to work in sectors of employment where they are solving problems the way a physicist solves problems. And that is very important in many, many areas of technology and science and engineering. And so there's a whole universe of jobs, but you just have to be flexible, have an open mind of what you might do in the future. But being a physicist, it gives you, in my view, a heads up towards success, even if you're not doing general relativity. So that's my message.
Professor Will, thank you very much for your time. It has been a pleasure. Have a great day. Thank you.
Thank you. Bye-bye.
Bye-bye.